morning, everyone, and welcome to today's webinar on the Wood-Pellet-Fired Biomass Boilers. And before we get started with the webinar itself, my name is Andrea Silvestri, and I'll be going through some webinar logistics. So today's webinar is based on a full report that you can find online at gsa.gov. And in addition to the full report, we have a 4-page findings, a 1-page infographic, as well as additional resources and guidance on wood-pellet-fired biomass boilers. In November, this is a part of a series of GPG Outbriefs. November's Outbrief won't be an Outbrief. Actually, the webinar will be more vendor-focused, and we'll be discussing this year's RFI, where we reach out to the private sector, educational institutions, and nonprofit organizations for technologies that we can consider testing in the GPG program the following year. This year, our RFI is focusing on 2 topics: behind-the-meter load optimization, where we're looking for technologies that provide on-site energy generation, energy optimization, and/or energy storage to provide resiliency and participate, so we can participate in cost-effective energy tariff programs. The second topic is improving overall building operations and maintenance. Here we're looking for technologies that can both improve tenant comfort and reduce operational costs. In particular, we're looking for products and tools that are outside the realm of EMIS platforms that can help us identify and prioritize, improve our physical or software systems in operational buildings. In December, our webinar will be on 2 next-generation chillers that GPG has assessed, the variable speed magnetic bearing chiller and the variable speed screw chiller. Both chillers were found to be 35% more efficient than FEMP-designated chillers and to have end-of-life payback under 5 years. Next year, our first webinar in January will be on socially driven HVAC optimization. This is a technology that uses input from occupants for dynamic temperature management, and the results showed that occupants were more satisfied with their thermal comfort, and at the same time, it saved energy. In February, we'll hold a webinar on advanced power strips and plug load control. And note that these dates sometimes shift due to presenter availability. Check back on gsa.gov for an up-to-date list of webinars, as well as recordings of past webinars can be found there. And we'll also be sending out invitations to webinars a month ahead of time. All of the webinars are now available for continuing education credits. You should receive a post-webinar survey with 5 questions after today's webinar, and one of those questions will be if you'd like to receive continuing education credit. If you don't receive the survey, please reach out to Michael Hobson. At the end of today's webinar, we'll be hosting an interactive Q&A session. You can enter your questions here in the lower right-hand side part of the screen here, the chat box there, and you don't need to wait until the end of the webinar to submit your questions. It's great if you can submit them as we're going along. And with that, let's get started with the webinar. Mike Lowell will be facilitating today's presentation. Mike, can we hear you? We're not hearing you yet.
Oh, I'm sorry, I was on mute.
Okay.
Good morning or afternoon, everyone.
Great. Thank you.
Welcome to the webinar. Next slide. In today's webinar, I'll be giving a brief overview of GSA's Green Proving Ground program. After this overview, Greg Tomberlin from the National Renewable Energy Lab and the primary investigator will summarize the research results from the Ketchikan, Alaska demonstration. Greg's presentation will be followed by on-the-ground feedback from Mondino Vini and Michelle Jones from GSA's Region 10. We will end the webinar with an interactive Q&A session, as Andrea just described. Next slide. GSA Proving Ground program was established to help our agency to make sound investment decisions in next-generation building technologies based upon their real-world performance. Next slide.
Mike hold on, I'm just getting a couple of notes that people have lost the telephone connection. Now I can hear you, so I'm going to, can people type in if you can also hear us? Okay, it might be some individuals. Great, thanks so much. Okay, continue on.
Okay. There's tremendous innovation going on within the industry. And of course, we all are constantly being challenged to do more with less. Innovation is what drives the efficiencies that let us achieve that. However, as shown by this graph with the valley of death, 4 out of 5 technologies never cross the technology valley of death. It's very difficult for those technology vendors to get from the R&D, stage of their technology development to commercial maturity. However, GPG helps bridge that gap by giving technology vendors real-world testing and informing the marketplace on the results. Next slide. GSA is committed to ensuring that GPG operates via a public, open, transparent process. Every fall, we host a request for information. As Andreas says, we'll be posting that this year's RFI in mid-November. And once we receive the applications from the RFI, we have 3 subject matter experts from DOE laboratories that score all the technologies that apply to the program. Shortlisted technologies are then invited to submit more detailed information that they present to a technical committee comprised of internal GSA stakeholders, as well as representatives from DOE and DOD. Finalists are then matched to a location within GSA portfolio of over 1,500 owned buildings that are best suited to validating real-world performance. Working with the DOE national labs, we then objectively assess how well the technology delivers on its performance claims, how easy it is to install and operate, what the payback looks like, and if it faces the tenant, how it affects tenant satisfaction. Next slide. And with that, I'm going to turn it over to Greg Tomberlin, who is the primary investigator for this technology. He's with National Renewable Energy Lab. Take it away, Greg.
Thanks, I appreciate that, and welcome everybody. Again, my name is Greg Tomberlin. I'm with the National Renewable Energy Laboratory in Golden, Colorado. Just a little bit of background on myself. I am a mechanical engineer by trade. I've been in the industry, engineering and design and research for about 3 decades now. I hate to say that, but I've been with NREL for about 6 years, and prior to that I've spent about 24 years in the industry with biomass projects and waste to energy projects primarily. And recently with NREL I've done a lot of work on biomass projects, some in Alaska and other places as well. Next slide, please. Today's topic again is wood-pellet-fired boilers. There's several different kinds of boilers that I've worked with in the past. Most wood burning, especially on small scale, consists of cordwood boilers or wood chip boilers, and then there's pellet boilers and sometimes also briquette boilers. Just a brief difference in some of the types. The cordwood boiler, again, as you can imagine, it's usually a small scale. It uses cut firewood basically. The fuel's fairly expensive. The fuel's high in moisture content. It doesn't really burn that efficiently, and it needs a lot of tending or a lot of people there to manage the systems. Wood chip boilers are by far the most common. Still, the wood chips themselves have a higher moisture content. They can be as much as 50% water in a lot of cases. So their heating value isn't very high, but the good news is that wood chips are accessible in most places. And then the pellet boilers, again, they're a lot easier, and we'll go through some of the technical aspects of pellet boiler technology, but the pellets primarily are higher in heating value, but they're a lot more expensive than just a simple wood chip boiler. Next slide, please. This is just a graphic of the system. Again, we did a project in Ketchikan, Alaska, where we installed one of these pellet boilers and then did testing. This is just a graphic. I don't really have a pointer, but I'll just try to walk you through what this looks like. Obviously, on the right-hand side is the pellet storage bin. Thanks for the pointer, whoever's doing that. One of the nice advantages of pellet boilers is to be able to get fuel easily and store it easily. So, you know, a truck can pull up next to this silo outside of the building and fill it full of wood pellets and then go on their way. You can fit a lot more pellets, a lot more tonnage, and a lot more heating value in one of these silos with a lot less room than you can with wood chips or cordwood. Those pellets have as you can see at the bottom of the silo, there's an auger. It's basically a small flexible screw conveyor that pulls the pellets out of the silo, and then it runs through the wall of the building. So the pellet and fuel storage is all outside. The pellets come through on an automated basis. These augers that feed the bins inside are automated. If there's a low level, it calls for more pellets and fills the bin up inside. There's a small bin, and I think we have pictures of that later. And then the pellet boiler itself is looking at the load. It can modulate automatically. That there's a small bin there that's got another small screw conveyor that augers the pellets into the furnace. That's done automatically. If the load goes up and it calls for more heat, auger turns faster and puts more pellets into the furnace. So very automated system. One of the nice things about these systems is they're automated. There's a picture of a guy standing there, but most of the time there won't be anybody standing there. When I was doing the testing at the facility, I was alone in this building most of the time because it's so well automated that you don't need a lot of people tending to the system. And if something does go wrong with the system, alarms can go off and then somebody can come take care of it at that point. Next slide. One of the things we just wanted to touch on was the pine beetle infestation kill. I'm sure you're all aware of. Again, on these projects, the wood fuel is a primary concern, and due to this pine beetle infestation, there's been about 18 million acres of forest where these trees have been killed. So that's a good fuel for one thing. There's a lot of it. Secondly is that a lot of these trees have been dead for a long time now, so the moisture content has dropped in them, so it makes them a better fuel all the time. And thirdly, I think, you know, the pine beetle kill is also a forest fire problem, so it's a good forest fire mitigation if that kind of wood can be pulled out of the forest and utilized in biomass projects. And again, it's got to be local. Wood is a heavier fuel, so transportation issues and that are an issue, but it's a very good feedstock, and there's a lot of it here in Colorado. Next slide, please. This is a slide where we wanted to show some of the advantages of using biomass fuel. And again, when you're using a biomass fuel or a pelletized biomass, you're really looking at competing with other fuels. Does it make sense to use biomass, or does it make sense to use heating oil or propane or other fuels? And one of the issues with the fuel is their volatility. And this graph is a little bit dated. It's from 2013. It was one that was used when the report was written, but it still shows the volatility issues. As you can see, if you have a wood system, your pricing is going to be pretty consistent across the years. There's not a whole lot of change in the pricing for wood feedstocks, whereas, as you know, oil, propane, and other fuels can vary quite a bit. If you look at from 2006 to 2013, there's some wild swings in fuel prices. And again, this is an older slide, so those fuel prices right now for oil and propane are lower, but still the point of volatility I think is made here. Next slide, please. This is a building in Ketchikan, the federal building where the biomass pellet boiler was installed. It's a hydronic heating system. They use hot water to heat this building. There is one biomass boiler put in this building, one pellet boiler, and the sizing of the boiler was right at 1 million BTUs an hour. There's also one high-efficiency oil-fired backup in case there was issues with the biomass boiler. They have oil for redundancy also. And we'll talk about this in a bit. It's a fairly large boiler system for this building. and that affects the economics. I think if it had been a smaller boiler, it probably would have had better economics as far as sizing the boiler to the building was concerned. Next slide. Okay, just to kind of overview the testing that we did when the boiler system had been installed, I think, for about a year. Claims are made on these pellet systems by vendors, as you always hear, and the boiler efficiency is key to the economics of these systems. And the boiler manufacturer was claiming 85 to 90% efficiency on the system. So I went to the site basically and set up a system basically where we would test it for a day. We tested, in essence, the temperature changes coming in and out of the boiler system and the water flow. We also looked at the amount of pellets that had been fed during that period of time. And then we also sent a sample of the pellets out to a laboratory to find out exactly what their heating value was. So once you have, in essence, the amount of pellets in and their heating value, that's the heat input to the system. Since we measured the flow of the water and the difference in temperatures, we knew the heat output of the system. So the heat output divided by the heat input gives you the efficiency of the boiler system. So after the testing, we concluded that the boiler was running right about 85%, a little bit better than that, which is within the claims. I think that it was also better than what we had expected, because during the testing period, the boiler was only running really at 45% of its rated load. And boiler systems are designed to run at full load, and their efficiency tends to drop off as you drop load. So running at 45% and still achieving 85% efficiency was, I think, a success. I think if it had been running at 80, 90, or 100%, you'd see even a better boiler efficiency than that. One other comment, I guess, I showed at the bottom too, we talked about the boiler sizing. It was only running at 45% load at this point, but if you look at the total output that boiler is capable of during a year, it's only really 13% of its capacity. The heating load during the year, in other words, at Ketchikan, is only 13% of the heat that really could be put out for this boiler. So in essence, the boiler was fairly oversized. Next slide, please. Operations and maintenance, that we're going to talk about more, I think, later in this presentation, is key to these systems. One of the reasons is just from a cost standpoint, there's people that have to tend to these systems. If you're looking at a chip boiler, for instance, if you're burning 20 tons per day, you may need 8 employees to run a 24-hour operation at 20 tons a day. But if that system was only 10 tons per day, you still might need the same amount of employees to operate the same system. So in essence, your costs are doubled for operations, just for the economy of scale. So that's a key part of the system. That's a key part of the cost. If you look at a pro forma for these systems, especially on small scales, the labor to operate them is very important. So the pellet system, again, the fact that it's automated is one of its key economic issues here. The fact that the pellets cost more is something that needs to be overcome, and the way they try to do that, or the way they can do that, is by using fewer people to operate the system on a regular basis. So these systems, again, have alarms that can go off to let somebody know they need to come over and take a look at the system. They can be automated remotely and controlled remotely. They have systems, the feed system, as I mentioned, doesn't take people to deal with offloading and getting material moved around a lot. The pellets go into the bin, they're augured into the system. Sometimes with chip boilers and other systems, you need to clean the boiler surfaces from ash and that kind of thing. This was actually an automated ash cleaning system where they could clean the tubes online, and that happened, I think, about every shift, every 8 hours or so. The system would shut off temporarily and it would clean itself. Ash removal is automated as well. So In essence, there's really nobody in the building to monitor the system for the most part, and the savings in operations and maintenance is really key. And the fact that it's automated, you know, again, it adapts to the system conditions, changing loads, that kind of thing. It reacts fairly quickly. Solid fuels don't react to changes in loads quite as fast as a natural gas system or an oil system might. But with these pellet systems and this auger, it's pretty responsive. And again, it was pretty overall stable system, and we'll get some more input from the people on the ground to talk to that later in the presentation. Next slide, please. So we did our test to look at the efficiency, and then at that point we wanted to look at some of the key factors, some of the key economic factors. So two of the key factors that we discussed, of course, is the fuel cost. What are the pellets cost per ton? And then also, as we discussed, the economy of scale, so the system size. And this is a small system, harder to make work economically a lot of times than a larger system is. So we put together kind of a little sensitivity chart here. To do this, we had to set a couple of things at the outset. One was we set the diesel price at the time, which was $3.63 a gallon, and it's quite a bit lower than that now. So this chart, you know, the payback in years that's shown here aren't accurate, but again, with the volatility, that diesel price, especially in some remote areas like Alaska, could very easily go up in the next few years as well. And we also set the capacity factor of the system at 75% capacity factor. So the table basically shows you the payback in years for some of these systems, and as you can see, if you look at the top row, it shows the pellet cost per ton, and obviously if pellets cost more, it's going to take almost a linear payback problem there with higher fuel costs. The thing that I think is probably more telling is as you look at the vertical axis, the system size and the payback. So if you look at the center column where pellets are $300 per ton fixed, if you're at a small system at 500,000 BTUs, it's a 6.5-year payback. But that system was larger, like a 4 million BTU system. The payback's less than half just due to the economy of scale. Next slide, please. Just to kind of review the variables that affect the payback and the overall economics of the system. Again, biomass fuel cost, of course, is very important. In remote areas that we look at some of these systems, pellets, there's not a lot of pellet manufacturers, and in some cases the pellet manufacturers and the pellet users are kind of a codependent relationship. In other words, people won't necessarily put in a pellet mill unless they know they've got pellet projects and vice versa. So that's key to keep the cost in line. And under the same concept, if you're in remote areas, the biomass fuel delivery costs are important. Biomass delivery cost is a function of diesel prices because usually diesel trucks deliver them. And this changes a lot, but a rule of thumb is you typically like to be within 50 miles. It depends on project size and other things, but get any more than 50 miles away from your fuel source and it starts to get expensive for delivery. And I think we base that on a transportation cost, again, a rule of thumb of about 15 cents per ton mile. And that could change with diesel price costs as well, of course. Heating oil costs, again, this is what you're competing against. You might have a project that makes sense, but when heating oil costs are low, it doesn't pay off as quickly, and if they're higher, it does. And again, these prices are older from the report, so that changes. But again, talking to the volatility of heating oil costs, a lot of times people look at the heating oil cost at that particular time when they're looking at a project, and if it's low, maybe a project doesn't make sense, and if it's high, maybe it does. But you have to look at the overall term of the project in 20 years and what the volatility might be. Heating oil consumption is something we look at too. If you're in a remote area, colder climates basically that use a lot of heating oil, that gives you a better capacity factor for your system. In other words, if there's only a 3-month heating season, you've got, in essence, a lot of capital costs sitting there not being functional for that season, so these work better in colder climates. Economy of scale, again, we discussed, the bigger the project, the more economic they are. And proper boiler sizing is another thing that's really key. There's a rule of thumb, and I've heard several different rule of thumbs that size it at 60% of what your peak load is. I've heard 75% or 50%, and that varies. I think if there's load data available for a project, it makes more sense just to run that data and optimize what is the best sizing, because that capital cost outlay could be a lot of wasted capital if you've got a project or a boiler that's way too large, and if it's way too small, you end up burning too many of the alternative fuels as well. Next slide, please. Again, just to wrap up, these systems are suited for hot water facilities. Typically, if you're using a biomass fuel, you're probably displacing fuel oil. You don't want to look at projects primarily where natural gas is an option. Natural gas prices, as you know, are very low now, and natural gas is easy to put in place. So most of these facilities are going to be optimal or going to be economical in colder climates and more remote facilities or more remote areas. They're best, in areas like Alaska. They work often and have been utilized in the rural Northeast and other places like that. So we're looking at cold climates and remote areas where natural gas is not available as the primary concern. That's my wrap up. With that, I'm going to turn it over to Marty Novini, who will give us some feedback from the actual operation of the system on the ground.
Thank you, Greg. Good morning, everyone. This is Marty Novini. I'm the Region 10 Energy Program Manager. I've been with GSA a little over 6 years. I joined GSA as a mechanical engineer about 6 years ago, like I said, at the tail end of this installation. My background, I've been in mechanical engineering and energy business for approximately 30 years, building commissioning and system verification for the most part. Next slide, please. Generally, operationally speaking, design engineers, mechanical engineers tend to size mechanical systems based on peak heating or cooling loads. And as we all know, mechanical systems run at peak operation maybe 10% of the annual hours or less. This generally tends to oversize building systems, building mechanical systems, and as Greg mentioned in his presentation, that seems to be the same case at Ketchikan as well. The building boiler is not grossly oversized, but it's oversized, and it's impacting its economics and its operation as well. On the hindsight, if I had control, I would have sized this boiler at about half capacity that it is right now, and that would have definitely impacted the operation and economics of this project. I am aware of other sites nearby in Ketchikan that have biomass boilers. They are grossly oversized and they're having operational issues as well. Next slide, please. One major factor that you have to consider with biomass boilers is that their control is a little bit different from conventional boilers that we're familiar with. Natural gas boilers or fuel oil boilers are a lot easier to control, meaning that you can modulate the heat output fairly easily by modulating input fuel. In terms of biomass boiler, you cannot adjust the heat output as easily as you could with other type fuel boilers. And that's essentially the crux of operating this kind of a system. When you feed the fuel into it, you cannot take it back. You have to use it. and that fuel continues to add heat into the heating system, which can easily overheat the heating hot water supply to the building. In essence, oversizing is more of an issue than undersizing. It's a lot easier to undersize a biomass boiler and have a backup boiler like a fuel oil boiler as a trim boiler that closes the gap between what you're providing and what you need to provide. And that to me would have been a lot better operation in the building and would have led to a better economic outcome out of this project. Also, on the hindsight, I have to mention Ketchikan in southeast Alaska gets about 140 to 150 inches of rain a year. And as we showed, the silo is directly outside in the elements. We do have a cover on top of the silo. However, it would have been a lot easier to put a better cover on top of that silo to prevent rain from getting inside the silo when we were filling it up. Moisture content of the fuel, wood pellet is directly proportional to efficiency of the boiler, and it affects the heat output of the boiler as well. In terms of operation of the building and the boiler, I think Michelle Jones is more qualified to answer your questions and present it to you. Michelle, are you online?
Let's see, Michelle, we're not hearing you right now. Michelle's typing. Just hold on a moment. I'm wondering, while we're waiting for Michelle, Michelle's going to dial back in. Mike, do you want to, we had a number of questions that are coming in, maybe as we're waiting for Michelle to dial back in. Do you want to, let's start with some of that Q&A.
Okay, let's get started with that. So first question, John Malone asked, how long will the pellets in that silo last? Marty, I don't know if you can speak to that, or Greg. I'm sure it depends on size of silo and run rate.
Speaking to Michelle, she typically orders new pellet to fill the silo at about 40 to 50% capacity. So I believe she fills the silo like once or twice a year.
Okay, thanks. And Bill Flay asked, is there a fire alarm or suppression system as a part of the overall system? You know, Marty?
Not more than typical. Essentially, the silo is sitting outside, and it's there's an auger that brings the pellet directly into the boiler. So it's not anything more critical than a typical mechanical room, I would say.
Okay, thanks.
Mike, before we go on, because that sounds like it might be helpful to have Michelle on the line, I'm going to, Michelle, we can't hear you now, is that correct? You're speaking? Yeah, I'm going to try unmuting everyone and see if that works. So for everyone who I unmute, make sure you mute your phones. We'll see if that works. Hold on.
Mute off. All guests have been muted. You can unmute your line by pressing *6.
Can you hear me?
All guests have been unmuted.
Yes, we can.
Oh, wonderful.
Okay,
Sorry about the
Michelle, can we
technical
hear you?
difficulties.
Okay,
Can you
great.
hear me?
We can hear you. So, okay.
Okay, so sorry about that little hiccup. It, let's see. Can we go ahead and just jump to the next slide? I'll try to keep us on track and make up for the little time loss. Okay, so for regional goals, as you can see from the slide, there are several facilities in the Ketchikan area that have made the switch to biomass as their primary heating source. And I think this is exciting for sustainability reasons, and I hope that the trend continues. If it does, it'll only continue to strengthen the local economy and ensure that our source for pellets stays strong well into the future. Go ahead, next slide. So we've talked about the volatility of fuel oil prices, and as you can see from this slide, we're experiencing that. This is a little bit updated information on fuel prices. In recent years, we've experienced both spikes and downturns, and right now we're in a price downturn for oil, but it isn't expected to remain as low as it is now. And the nice thing about the pellets is that they're sourced and made locally, so if we do have issues with fuel oil, in terms of availability and price spikes, we don't have to worry about relying solely on something that has to get shipped in. We have that fuel source there locally. And in remote Alaska, that's key. Okay, next slide. So as you can see from this one, the biomass boiler doesn't run in the shoulder seasons. It needs outside air temperatures to be consistently below about 45-50 degrees to operate efficiently. And as Marty was saying, you have to practice a little patience with the system as the warm-up and cool-down periods do take longer than with an oil fire boiler. For warm-up, from the time the biomass boiler is programmed to start bringing the building up to temperature versus if you were using an oil fire boiler, it does take longer for the biomass boiler to come up to temp and heat the loop. This isn't problematic, but it's just something that you have to be aware of, especially when you're programming your building automated system. The same is true for cool down periods. The pellet fuel, once it's fed into the system, it has to be burned before the system can actually start cooling down. And as a side note, if you are going to take the biomass boiler offline for maintenance, you're going to need to give it at least a good 24 hours for everything to cool before you get in there to do your work. Next slide. There is a learning curve for maintenance technicians to understand differences between the oil fire boiler and the biomass boiler. And something that has helped shorten that, in my experience, is having a good handoff period from one technician to the other, as well as keeping a log of maintenance so that technicians can reference past notes to see if there's been an issue experienced before, and if so, how was it handled. For biomass boilers, preventative maintenance is important. One of the issues that we experience and we want to avoid is clinkers. First off, what is a clinker? A clinker is when there's a buildup of ash in the system, and that the buildup of ash comes across the grate in the combustion area and eventually can restrict airflow, which will lead to increased temperatures, melting that ash, and it solidifies into a clinker. And how does that ash build up? Clinkers generally occur for a few different reasons, mainly poor quality of fuel, or if your boiler isn't being cleaned out regularly. With this one, there is an automated system where it helps push all that out. At the same time, for preventative maintenance, when the ash bin is cleared, the O&M technician is looking for the status of clinkers. If there's an increase in that, you want to make sure that everything is running and do a little digging and make sure everything's running. As it should. The big when everything is is uh, uh, taken down for the heating season uh, uh, and taken apart